Now we can. All right, good. Let's start over. All I was saying is that we're going to talk about springs. So we started out with Coil Springs, and we're going to stay in Coil Springs today. Wednesday we'll move into spring fatigue, and then Friday we will move into all the other types of springs. That's why I was showing the variety of the torsional type springs and the extension springs, which we haven't talked about yet. So we'll do all of that later. Today we're talking still pretty much compression coil springs. So what we're interested in is some springs have to operate, they have to operate, close and open at high speeds. I'm thinking sort of the springs in a valve train in an engine, a car engine or a truck engine. They could need to operate by being squeezed over and over really quickly. And if you get the wrong frequency of that, you're too high of a frequency, you'll enter the fundamental frequency of this spring, depending on its geometry. And then it can have effects such as spring surge. You can actually get valve floating, is what it would be called in a valve train for an engine, but where you're trying to squeeze this spring at such a rate that the stand-in waves and the surge in the spring will actually cause it to lift off of the seat that it's on. And now the spring is actually kind of floating in air there, which is certainly not doing what it's supposed to be doing. And so we want to avoid all of those frequencies. And then I was over here, and this is where we left off. Chapter 10.8 is the critical frequency of helical springs. There are a couple of definitions for variables. Most of them are things we already know. And then there are a couple of equations over here that we need to calculate. And I think that might be the last. Well, there's one sentence on the other page. Actually, the sentence on the other page is pretty important because it gives you, in the text here, it gives you the range. 15 to 20 times is how many times below whatever we calculate. So we're most concerned with the first fundamental frequency. There could be harmonics of it at higher frequencies, but we really want to stay 15 to 20 times beneath the first fundamental frequency. So we're going to calculate the first critical frequency, and then we want to be 20 times below that in order to not even get close to the resonance frequency of these springs. So that sentence is important. Here are our equations. Got a couple for calculating frequency. We've got one down here that actually calculates the weight of the spring. That's going to plug into our frequency equation. And so it's going to be really straightforward. We're going to go over to MathCAD and do this part. Let's see, let me get this one. Yeah. So here's a couple of coil springs that would be in like a valve train for an engine. Now the ones in the picture over here, you can kind of see they're a little bit tapered. This first coil is a little bit smaller than the others, so they have a little bit of variable frequency or variable spring rate to them. We're thinking more of one like this, where all the coils are the same diameter, and this one, it would be closed and ground. You can see how that last coil on the top and bottom of it have been closed over, and then it's ground flat. So this would be closed and ground and a compression spring. So what we need to do is I need to find my notes, and then we can start writing some equations for this. Let's see. Let's start with equation 1025, which is just we're not going to be able to solve this one just yet, but we'll be able to, well, let's first look at the difference in these two because there are two that look almost identical, two equations. So we have both of these equations. One of them is 1/2 of this quantity, the other is 1/4, and the difference is the one down here, 1026, is one end is against a flat plate and the other end is free. So we are kind of in that realm with the coil springs here. One end, where's my mouse? One end is against the flat seat down here, and the other one is sort of free, but not really. I was going to say that this is constrained well enough to be in this category up here, because it's not just completely free at the at the top end here. It is constrained by the valve stem, the rocker arms pushing down on it. So we're going to use the one that's basically constrained on both ends, always in contact with the plates, which is pretty much what we've got for these valve stem or these valve springs in the picture that I've got. So there are two of these, and so be careful with which one you're using. We're going to use the 1025, which is probably, I don't know, 80% of the time the one that you're going to use. So let's start with that. I'm over here. Here we go. All right, so frequency is equal to 1/2, and then that's going to be multiplied by the square root of K spring rate, which we are going to have to estimate using the equation that estimates spring rate for coil springs, times G, that is acceleration due to gravity. So this is one point I'll make. If you're doing these by hand, then G, and you're using US units, it's going to be in feet per second squared, and a lot of these other units are going to be inches, or they're going to be related to inches, so you will have to convert G over to inches per second squared instead of feet. And then here we just have, they use capital W for weight. You do have to also, if you're writing this out by hand, you have to be very careful, because we have weight here. In fact, you might even want to spell out, weight. Well, if you can spell weight. But you also have omegas sometimes, not necessarily with the spring so much, but when we do the shafts, you'll have omegas. And so you might want to make sure you're writing W's or spell out weight or whatever. We don't have any of these defined. Now, it thinks we do. Actually, I guess G is defined by default. So, but we're just going to start with that and figure out all the things we need to plug into here. So the spring rate is estimated with, let me see if I can find the equation. Where is it? 10.9. So equation 10.9 is going to estimate spring rate. And again, I'm going to put equal sign, but in your book it's an approximation. It comes from the energy methods, and they make a little bit of an assumption there to calculate it, or to estimate it. D to the fourth. Now this is going to introduce a whole set of other variables that we got to go find. So the lowercase d is wire diameter, so we'll have to find the wire diameter for the spring. G is modulus of rigidity. 8 mean coil diameter, we'll have to go find that. Or these will be things we could measure if we had the valve spring in front of us. We could just measure them. And then times the number of, well, I'm in the, there we go. Number of active coils. All right, so those are mostly parameters that we can either define or measure. So I did go and pick out an actual valve spring set of numbers. So the wire diameter for this one, D, lowercase d, is 0.171 inches. So that would be, how large of the diameter is the wire itself. The OD, so the outer diameter, not the diameter capital D that goes in spring rate, but the outer diameter of the spring, it was 1.285 inches. And you can certainly get all of these details off of a valve spring manufacturer. They have all of these pieces of information available. So mean coil diameter is going to be the outer diameter minus the wire diameter. It's, technically it's the outer diameter minus 2 1/2 wire diameters, but that just adds to 1 wire diameter. Let's have that in inches. We need the number of active coils. So if you look at this picture that we're using, this is closed and ground. So the total number of coils, 1, 2, 3, 4, 5, 6, 7. But then closed and ground, you subtract 2 to get active coils. If you don't remember that, table 10.1 has all of that. So closed, or they call it squared and ground. A lot of times I call it closed and ground, sorry. So squared and ground, number of active coils is Na plus 2. Active coils plus 2 equals the total number of coils. So we'll do it that way, where we have total number of coils, we count them from the picture, was 7. And number of active coils is number of total coils minus 2 from table 10.1. We will write that. There we go. What else do we need? Is that all? Oh, no, we need a value for G, modulus of rigidity G. So this is just going to be from a table. You can get it from a lot of different tables. Table 10.5 does have these. So right here, there are values for modulus of rigidity for various materials. We would need to know the material that the valve spring is made out of. Now in this table, there's actually one called valve spring A230. So we'll use that one, 11.2 million PSI. Let's see, make sure I'm active over here. 11.2 times 10 to the 6th. Wow, having a bad day typing. 11.2 times 10 to the 6th PSI. Oh, really bad day typing. There we go. Let's see what our spring rate is. But let's have it in pounds per inch. 173 pounds per inch. Let's see what our critical frequency. Oh, we haven't calculated the weight of the spring yet. It thinks we have, but it's using watts there. So be careful with MathCAD because it does have built-in units, and sometimes you can create a variable name that is a built-in unit. So we don't want W to equal watts. We're going to have W equal the weight of the spring. And they have an equation in your book for calculating the weights of the spring, or at least estimating it. I'm just looking at the equation number. 1027 down here is the equation number. So basically what it does is it calculates, you can see a pi d squared over 4 in there. So there's a cross-sectional area of the wire itself. There's another pi d, that's basically a circumference, number of active coils. So that gets you the volume of the spring more or less. Now it's not really counting the fact that the ground ends, well, I guess I said that wrong. These are the active coils because when we're talking about the frequency, the critical frequency, it's only the moving parts that matter. And the active coils are complete coils. They're not, the ground part isn't active, you know, it's just sitting there. So it is the number of active coils. And then they've got a, I can't remember exactly what they use. Oh, they use specific weight here for gamma. Basically the density, except it's calculating a weight instead of a mass. All right. So let's plug that guy in. We'll also need that gamma value. So W is pi squared times wire diameter squared times mean coil diameter times number of active coils times, whoops, oh, I lost my cursor. Oh yeah, gamma over 4. Oh yeah, we need the 4 because we calculated the cross-sectional area of the wire, pi d squared over 4. All right, now it thinks we have a value for gamma, but we haven't actually plugged one in. So let's plug one in for this. We could also get this from 10.9, I believe. Let's find out. No, not table 10.9. No. well, I have it written down. It is, it's table A, oh, it's A5. I was looking in 10. We'll go look it up now, just so we can see it. There we go. So here's table A5 with our, they call them unit weights here. And we're going to use like a stainless steel is probably the closest one that we could pick from these choice. Definitely not aluminum or copper or brass. And so valve springs they are a special steel. There is a nickel steel in here and a molybdenum that we could also use. We could probably, a lot of them are like a chrome moly type thing. Let's just use the stainless one, 0.28. So you have to pick the right material for your spring to get the right specific weight for it. So it was 0.28 is what it was. Well, let's plug that in over here though. And then it's going to have units of, I think that was pounds per inch cubed was what we have to look in the table. I'm pretty sure it's pounds per inches cubed. All right, now we have done all of the things necessary. We've got our wire diameter, our mean coil diameter, number of active coils, a couple of material properties. We estimated our spring rate. So it takes 173 pounds to close this spring an inch. Now, the valve springs in pretty much any car that you're going to drive don't open an inch. So you're not actually having to push on this spring with 170 pounds. Then we calculated the weight of the spring. And here we should get a critical frequency. This comes out in hertz. In fact, we could just write it as hertz, 1/2. So this is not a radian per second. This is a hertz. Now, it did say that we have to operate 15 to 20 times below this one. So let's be the most conservative and divide it by 20. And put hertz in there. 19 hertz. So 19 cycles per second is what is safe to operate this spring, and we're far away from any of the fundamental frequencies. Now, this, it's kind of useful, except that if we're talking about an engine, you normally don't talk about how many hertz the engine is running. You talk about how many RPM the engine is running. So we kind of need to calculate the RPM just to finish out our calculations here. So let's critical engine RPM. So for this, a typical engine is going to have every time I don't know how much you know about engines and how they work, but there is what's called a camshaft. We can't see it in this picture. That operates these push rods right here. You can see the top of one of them here. The push rod pushes on this rocker arm, which pushes down here. They're pivoted on this fulcrum right here. And pushing down on the rocker arm opens. You can kind of see in the middle here, there's a silver rod. You can see it better in this side. That's a valve stem, which the other end of the valve stem is the valve itself. And that's how either fuel gets into the chamber or exhaust gases get out of the chamber. So all that to say that this push rod is going to operate, the engine is going to rotate twice for each rotation of a camshaft. So the critical engine speed is going to be, what did I call it? F allowable, I guess. Whoops, equals F allowable. So there's our allowable frequency, and it's in hertz. So RPM is revolutions per minute. So let's multiply times 60. And then we're going to need the fact that the engine rotates twice for each one of these camshaft rotations. So times 2. My units may not work out here. I might have to, so it's still in hertz there. Let's just divide the hertz out. And there we go. 2,300, and this would be RPMs. I guess I could put the 60 as minutes and make it figure out revolutions per minute. This is just simpler for me. So these are RPM. And if you notice, this is kind of a just generic setup here. But you'll see a lot of times, this is a little bit low, of course. You can operate your engine RPM faster than this. But this is the most conservative. We could have gone down to 15 here, and then we're at 3,000 RPM. But you really will have different engines, depending on how they're built, will have different red lines. So at some point, on your if you have a tachometer in your car, then it will have a red area where if you get the engine rotating that fast, bad things are going to happen. These are some of the bad things that could happen. You could have valve float where you hit the fundamental frequency, or you're getting close to the fundamental frequency, still 15 times away from it in our setting, in our calculation right here. But you're getting close enough that you can begin to be concerned about it. Because once you have these springs right here, if this spring comes off of this seat, now your valve is not operating the way that you anticipate it to operate, and you're going to get all kinds of bad things happening. And so that's one of the places that number comes from. Okay, so this part down here, calculating the engine RPM, that's not really necessary for what we're talking about. Just calculating this allowable critical speed or frequency for operating the springs. And so the equations are actually really straightforward. Spring rate, the weight of the spring, which if you just thought about it, you could create this equation without even knowing it. It is the weight of the active coils in the spring, so you don't have to worry about the fact that some of them are flattened out, possibly. And then the little 1/2 square root of kg over W calculates the fundamental frequency, and then you want to be 15 to 20 times less than that. So it's not a complicated matter to calculate that. All right, let's go on to critical speeds and shafts. In fact, let's create a new page so that we don't end up with any accidental variable overlap between these two. All right. So this takes us back. So now we're departing from springs temporarily to go back and pick up critical speeds of shafts, which we skipped over way back at the beginning. So we're going back to chapter 7 with the shafts. And let's see, I think this is chapter 7.6. Now, this chapter, unlike the chapter that we just looked at for the springs, there is a lot of stuff going on here. They do a lot of derivations, very thorough derivations of stuff. They show a couple of different ways that we can do this. We're going to basically pick up, let's see, where do they have it? Down here, equation in the 730s. We're going to use these. And we'll use this 733 over here. And then we need one other equation that I didn't see right away. Well, I guess it's right here. 724. So what we're going to use are these deltas. These deltas are influence factors. And what they do is, well, if you look at the form of it here, let's zoom into that. So this delta, there's actually a piecewise function right here, but let's look at the top one for 724. What that is, if you look at it, you might have seen that, and maybe even the 6EIL in the denominator rings a bell. This is basically the equation of elastic curve for a beam. And that's what we're doing here. These deltas, what they're going to do is they're going to take whatever kind of setup you have, in this case, a simply supported beam with an offset load, and they're going to take all the elements that might be on a shaft. So a pulley or a gear or some kind of hub or something like that. It's going to take that pulley or hub or whatever the element is, calculate its influence. So that's what the delta is an influence coefficient. And it's going to say that if we have a shaft 7 inches from the end of or a pulley 7 inches from the end of the shaft, which we're treating as a beam, then this is its influence coefficient at that point. And the ultimate goal is going to be to take all of the elements on the shaft and translate them to the center of a shaft and calculate, okay, if all of these elements have their influence coefficients at their own locations, translate those over to the center of the shaft and calculate the fundamental frequency from there. So we're going to use this type of equation. These are good when you have a simply supported shaft, but if you have a cantilevered shaft or other things, then you would need to sub out the appropriate equation of the elastic curve for a cantilever beam instead of a simply supported beam with offset point load. All the ones that we're going to do are going to be simply supported beams with offset point load, so we can use this one. We don't have to go drag out other beam equations. Then we're going to go down to these omegas. Now these, so when we did the springs, the critical frequency came out in hertz, cycles per second. These equations are going to give us omega, which are going to be radians per second. So we do have to make sure that we don't accidentally get confused. MathCAD should take care of those units for us, but if you're doing this by hand, it would be easy to accidentally think of these as hertz also, but these are going to be radians per second. And then we'll combine it with the last equation over here. Actually, this equation, the top part of this 733, where we've got a speed squared, or angular speed squared, and then some other terms over here that we'll get to. All right, so let's see how all this works. First, we need to draw up a shaft that we're going to deal with. I have one that's just going to have 2 pulleys on it, and just to keep it relatively straightforward, but this process is going to work no matter how many elements you have on a shaft. I will say that this is assuming the shaft itself can be at least approximated by a straight shaft. It doesn't have steps in it or anything. Once you start adding steps in larger sections to the shaft, then you may even have to treat those as extra weights, which are distributed, which is a little weird. So this will give you an approximation. It won't be exactly what you could calculate in a numerical solution of some sort. So here's going to be our shaft, and again, it's going to be a straight shaft, all the same cross-sectional area from one end to the other. We'll have some bearings on it. Oh, here we go. We're going to put the bearings at the 2 ends. And then we're going to have 2 pulleys or gears or whatever you want to call them. One of them is going to be, just going to draw it as a block here. And the other one is going to be a little bit smaller and here. Now, that we're also assuming that we have built this thing as balanced as possible. Now, if you have something that's an unbalanced shaft, that is going to drastically affect the critical frequency, because now you have this eccentricity that's also rotating, and that's going to create a whole new set of problems. And in general, you don't want that in at least shafts that rotate very fast. You want the shaft to be balanced. So we're going to assume we're starting out balanced. But if you're not, then this method it'll work, but the calculated number here is going to be well above the actual frequency that you would need to operate below. This we're going to put, I think I said 7 inches here, and then I'm going to measure this all the way to the end and have it at 31. So our shaft is 38 inches total. Here, I'm measuring or showing my dimensions in a weird way just because these are the dimensions that we're going to need in our equations. This would make this 28. So we have 38 inches either way. We're just measuring to the individual pulleys. We need the weights of these things. Let's go ahead and put that. Let's say that this guy's 8 pounds. That one's 5 pounds. And then we also need, this is going to be a 0.5 inch diameter shaft. So pretty thin shaft for 38 inches long with 8 pounds and 5 pounds on it. So the overall scheme of what we're doing here is we're going to calculate that delta. We'll call this gear 1. And this will be 2. So we're going to calculate a delta 1,1 for the 8-pound gear. That is going to be the influence coefficient of this gear at this location, location 1. And then we're going to use our equation. I don't remember the number. We'll look it up in a second. Our equation to translate this effect over to the center of the shaft, because obviously if I have a force here, the whole shaft is, you know, if I think of this as a simply supported beam with a point load right here, the whole shaft has some amount of bend in it. And the delta 1,1 refers to gear 1 at location 1 basically, but we need to move it over to the center. Same thing here. We'll do a delta 2 at location 2, and then our equation will translate this effect to the center of the beam. Basically what it's going to do is what size weight do we need to put here to have the same effect as an 8-pound mass over at point 1. It should be a smaller number, right? Since I'm moving 8 pounds to the center, I need a smaller force here to have the same effect at the center that the 8-pound does when it's over towards the edge some. You know, you could think of that. If I move this 8-pound all the way to the end, then it has almost no effect on deflecting the center of the shaft, because it's pretty much all just a shear load at the bearing, more or less, if I move this all the way over here. So if I do the opposite, to move this to the center, I need a very light weight here, less than 8 pounds, to have the same effect as this 8-pound gear over here does. So that's what our first calculation is going to be, is what's the equivalent weight that we can put right here for each of these, you know, the 8 going to here and the 5 going this way. What's the equivalent weight that I can put here to have that same effect? So that's what we're going to do first. Let's set this up in MathCAD. I do have MathCAD pulled up here. All right, let's define a couple of our terms that we're going to need. I said it was a 1/2 inch diameter, so that's going to be R of 1/4 inch. I didn't say what kind of material it is. Let's just say it's a steel. So 30 times 10 to the 6 psi. Oh, really don't like how it's operating there. We're going to need, these equations had I in them. Remember, the beam, it's basically a beam deflection equation, and that's certainly got the moment of inertia in it. So moment of inertia for a round shaft is pi times d to the 4th over 64. Oh, I don't have d. R to the 4th over 4. Or d to the 4th over 64. Spread this out a little bit. We need L. 6EIL is in the denominator, so L is 38 inches. That was from our, wow. L equals 38 inches. That was from our picture we drew. I think we will also need A at some point. So let's go ahead and plug in A. This is just the cross-sectional area. We'll use pi r squared. And obviously you can use the diameter. I just never set up the diameter equals 2r. All right, so those are all things that we need to get started. Now we need to plug in our influence equation. So let's set up the generic one, which is equation 724. I'll show you that one. So this top equation with the bx, 6EIL, L squared bx, all of that, that is the equation of an elastic curve for a simply supported beam with an offset point load. And the only thing that's missing from here is there's no F. So this is assuming that it's responding to a unit force of 1. So that's why there's no force in this equation. But we're going to create this equation in MathCAD. I think I will just set it up as a... oh, I don't remember how to... Oh, shoot. I was trying to do an index. I don't remember in MathCAD Prime how to do an index. Let me see if I can find it. I don't see it right away. Well, we'll do it the other way. We'll just plug them in as coefficients. So now the equation is b times x. We'll have to define b and x in here, so we'll do that in a second. B times x over 6 times e times I times L, all of that term, times L squared. I think they use a lowercase l in your book, but this is the length of the beam. L squared minus b squared minus x squared. Oh, the other thing that... Oh, I don't want to do that. The other thing you'll notice in a lot of these equations is this term right here that we're typing, the L squared minus B squared minus X squared, is actually written the opposite order, and they're all plus, I believe. Or maybe it's X squared plus B squared minus L squared. The difference is the direction of the deflection. So is the deflection positive when it goes down or positive when it goes up? So it's the same equation. Let's put B and X in here for this equation. So B in this equation is going to equal, let's see, 7 inches. And I'll look at the diagram in a second. And that will make X 31 inches. Okay, so it's just one of the distances, and we could have done it the other way. I guess we could do it in 31 and 7 as B and X. It just depends on which direction you want to measure from. So I put B as 7 and X as this direction, which means I'm measuring from this way. Or you could have done 31 as B and 7 as X. It doesn't matter which way you do them as far as this calculation goes. So what I get when I evaluate this is a weird set of units here. Hopefully they come out right in a second. So this should be, it's sort of like a spring rate. So spring rate is how much force you have to apply to get a certain amount of deflection. These influence coefficients are a certain amount of deflection per an amount of force. So I don't even know if, let's put some more decimals in there. All right, there we go. So we get 0.0449 inches per pound of force. And this is the influence coefficient of weight 1 at location 1. So I'm just going to copy that and do 2 at location 2. So the things that change here, it's the same shaft, so E, I, L, those all change, all stay the same, rather. But it's a different location. So here B is 28 inches and X is 10 inches. And you can see that here. So B, I'm measuring, well, X is coming from this way, I guess. So B is the 28 inches and X is measuring out to the 0.2, which is 10 inches. So I get a small number, but slightly larger, 0.0747 inches per pound. Okay, so those are our two influence coefficients. Now there's a third one I need to calculate, which is my ultimate goal is to take these two weights, masses, whatever you want to call them, these two gears, and calculate or translate their effect to the center. So I need to do the center's influence coefficient. So instead of 1, 1 or 2, 2, I'm going to call this one CC. So if the force is at the center, and I want to know the effect at the center. So the force is at the center and the effect is at the center. These are the forces at location 1. I want to know the effect at location 1. The force is at location 2, and I want to know the effect at location 2. So the center is just, I'm going to put B equal to the center of this shaft is 19 inches. And X would also be 19 because we're at the center. And so now I've got this influence coefficient at the center of the shaft. Have I already defined? Now, I never did define the actual weights that I was using. So let's put W1 is 8 pounds. So this is the weight of gear 1. And I made the weight of gear 2 5 pounds. Oh, yeah, 5 pound force. Okay. So now I can use the equation. I believe it is, where is it at? 733. Well, that's not exactly, where is it? Well, it's 733, yes. Okay. We're going to use 733 twice. So 733 is, there's 2 versions of it. We're using the bottom version right now. So what we have here is, what's the equivalent weight of, in this case, weight 1, so the 8 pound force, but at the center of it, the shaft, not at location 1. So this is the translating equation. And we're going to take the influence coefficient for force 1 at location 1, divide by the influence coefficient of a weight at the center, and then multiply times the actual value of the weight. And this will give us the effective weight. So we expect this, when we move the 8 pound weight to the center, it will be a smaller than 8 pound weight. So if we put a smaller than 8 pound weight right here, it would have the same effect as the 8 pound weight over here. So let's plug it in, hope we get a number smaller than 8. So W, oh, I use lowercase w, 1C. I think your book actually uses subscript. Well, no, they're just smaller. All right, so the equivalent weight is going to be weight 1 times delta 1 over, oops, over delta CC, and 2.9 pounds. So what this says is that if I take the 8 pound weight off and put a 2.9 pound weight here, that's the equivalent as far as critical frequency goes. That's what it says. We also need to do that for the 5 pound weight. So it's going to look exactly the same, right? Except this will be for weight 2. So we'll put in force 2 as a subscript. And then instead of 1, 1, we're going to do 2, 2. This one is actually heavier, but it's not moving quite as far. So we're not moving quite as far as we move the 8 pound, and it's a smaller weight to begin with. So it ends up that we need to put a 3 pound weight to replace the 5 pound weight. So we put a 3 pound weight at the center, and that replaces the 5 pound weight as far as critical frequency goes. All right. Then we can use our equation 733, but the top part of it. So you got to be careful with this. This one, oh, there we go. In fact, we might need to zoom in. There we go. So this is omega. So this is a speed. This is weight. So we're looking at this part of the equation right now. We're actually going to look at this part and the very last part here. And so if we have the weight of the translated weight, the influence coefficient at the center, acceleration due to gravity, we can calculate the square of the critical speed. If you're doing this by hand, you do have to be careful, particularly in US units, that you convert over 32.2 feet per second squared, because you've got inches built into these others, into the influence coefficient. All right, so let's go back over here, and let's calculate a total weight. Now this is the total equivalent weight, so after we've moved them. So this will just be 1C plus weight 2C. So it's just adding the two of these together. So not a big deal. Okay. Now we've got like a 6-pound equivalent weight in the center. So we've moved both of these to the center and added them together, basically. So now we've got this one weight that's 6 pounds at the center that should have the same effect as these two offset weights. And so we can calculate the critical frequency of this guy, omega. Oh, wait, I never remember which one is omega. There it is. This is the W key. All right, omega is going to be, well, let's write the equation down first, and then we'll solve it. So this is equation 733, the top part of that line, but I'm going to write it as just a symbolic equation so we can look at it. All right, so there's the equation we're solving. So it's the beginning part and the very last part. We're not using these intermediate steps. I guess you could, but we don't need those. All right. So what we need to do is basically just take the square root of both sides, and we'll solve for it. Now, don't be confused though, because this does show omega 1,1, but let me draw a picture just to reinforce this further. We have taken this and made this from it. Oops. So we still have our bearings on the ends. But now we have a single 5.9 pound element in the center of our beam. So that's what we've done, is we've taken this and converted it over to this. And we could have as many of these elements in here as we want. We could have delta 3,3 and delta 4,4. We can keep adding and adding and move them all to the center. And now this is the thing we're analyzing. And so when we're talking about omega 1,1 in this equation, there's only the one location. So that location is the center of the beam. So don't get too confused with the 1,1 here. It's not the same 1,1 as it was before. All right. So let's solve this. So we need omega. In fact, I'll switch it over to elements. So this is all of the elements have been superimposed at the center of the beam. It's equal to the square root of the equation here. So G over the total weight, which I call W total, times delta CC. Delta CC has not changed, by the way. So we can leave it the same. But those need to be subscripts for it to work out, I think. Now it gave it to us in radians per second. No, it gave it to us in 1 per second, but this actually should be radians per second. I wonder if it'll let me. Yeah, it will. Okay. All right, so 72.6 radians per second. Now, that's almost what we need. We're really close. But this is assuming that the shaft has no effect at all. So if we had this same thing, just the shaft with no weight on it, it would still have a critical frequency of its own. It should just be higher than this one, but it will have its own critical frequency. So we do need to calculate the critical frequency of just the shaft. We have the critical frequency of basically this 6-pound gear on a rigid but weightless shaft right now, and we need to combine those two things together. So let's do the shaft. That is equation 722, I believe. Let me make sure. Yes. So it's right here. So they give a critical speed of a shaft. So we need to do that first. And it's basically just based on the specific, so the weight of the shaft and the size of the shaft. So omega for the shaft equals pi over L squared. This is just reading equation 722. And it's the quantity pi over L squared times the square root of G. Wow, not like that though. Let's do like that. Square root of G times E. I think we put E in already. Yes, we put E in already. Times I over A. We did calculate A earlier. Times gamma, which I don't think we put gamma in here. We did not. So we have to go look up gamma again from table A5, just like last time. In fact, it's going to be a steel. That was a stainless steel 0.28 that we used. I don't know exactly what I used in this particular one. Let's see. I think I used the same thing. Let's just use that again. Gamma 0.28 pounds per inch cubed. So this number, hopefully, again, radians per second, 173. So somehow now what we have to do is we need to combine this and this. We need to combine those two critical speeds. To do that, there is equation 731, or 732 is more generic, I suppose. So it's equation 731 and 732 are the same thing, but we need to combine basically 1 over the critical speed of the combination is approximately equal to 1 over the critical speed of each part added together. Now, they go through equation 730, kind of has all of these here. What it says is that as you get higher and higher terms here, you can approximate it with just the first critical speeds. So what we need to do is basically take the overall, so omega overall, so the combination of the shaft's critical speed and the elements all translated to the center critical speed equals 1 over, or the square root of 1 over, which is the same thing as 1 over, because the square root of 1 is 1. 1 over the critical speed of the elements, which I called omega elements, I believe. Elements? Yeah, elements. Squared. The squared is only on the omega, not on the quantity here. Plus 1 over the shaft speed, critical speed, squared. Okay, I think that's it. Why is that not? Oh, look at that. I think I put W, not omega there. Which now it's stuck in, oh great. Elements. All right, so be careful in MathCAD. W's and omegas look a lot alike. And let's put it in radians per second. So it says 67 radians per second. I think I didn't know there's that way. So that's the combination of the elements at 72 and the shaft at 174. When you combine them, you get 67-ish radians per second. Now, all we need, which you should have, the combination should be lower. The way they're added together, kind of like springs in series, the combination should be lower than either individual one. All right. But there is a guideline. Let's see if I can find it real quick. Well, I don't know exactly where it states it, but the guideline is just like in the springs, we were supposed to be 15 to 20 times lower than the critical frequency. Shafts, we don't have to be but half as low. So omega allowable, let's make that into an actual omega this time. Allowable is equal to the one we just calculated, overall, over 2. So 33 radians per second. And we could probably also put that in RPM, because a lot of times you talk about shaft RPM. 320 RPM. So a little bit more involved to calculate the, oh, you can't see the MathCAD. Oh man, sorry. So let's see, where did we leave off at? Probably, I think we did this. Wasn't watching the screen. So just to recap from where, I don't know exactly where you couldn't see the MathCAD, but I'll go back and look at it in the video later. But I know we probably did this part where you could see it. So this is just the, yeah, because we talked about, this is where we went off the screen. Is where we talked about omega 1,1 being the new, I'm about to go off again, the new 1,1. So with the single weight, then we calculated the critical speed of just that. So this is the critical, omega elements is the critical speed of the just the element on a rigid but massless shaft. Then we decided that, well, we should include the shaft itself. So this is equation 724. Wrote it 722. So this is equation 722 in your book that calculates the critical speed of just a shaft. Now it is a solid shaft with no changes in geometry, so no steps or anything. Which that's a limitation of the way we're doing this, is that the shaft is solid. Pretty much if the shaft is stepped in a way that you think that's going to matter, then you're going to have to do a numerical solution on this to integrate across the whole thing. Basically take all the little pieces, translate them to the center. It's a whole big process. We're not going to worry with that in here. We're just going to get close. And then we had these two different speeds, or critical speeds, for the elements and the shaft, and we needed to combine those together. And we used this equation, which is equation 732 or 731. They're both kind of the same thing. And we did have to solve it for just omega instead of omega squared. And then we calculated this combination is the 67 radians per second is the critical speed for the combination of the elements and the shaft together. And then I said that there is a guideline that you should be at least, your allowable speed should be half or less of the critical speed that you just calculated. So we divided by 2. And then I switched over to RPM just because a lot of times you talk about shaft RPM instead of shaft radians per second. And that's where we left off. That's when I finally looked and you said we couldn't see the screen. All right. So at that point I was saying that it is a little more involved to calculate the critical speed of a shaft. It's not terribly complicated. There's a lot of little pieces you can get lost in as far as, you know, got to understand what the influence coefficients are doing. So the 1,1s and the 2,2s and the CCs, what do those subscripts mean? And what they mean is this is the influence coefficient of the force at 1 at location 1. And this is the force 2 at location 2. This is the force at the center, whichever, we just called that the force at the center, and its effect at the center. Then we calculated the equivalent weights that you would have to have if you moved all of the elements to the center. We added them together, and that's when we started doing the speeds part. So it's a little more involved in the spring critical frequency, but doing it by hand, there are some little traps you can fall into, particularly with the units on G in the US system, because it's going to have feet per second squared, and these deltas have inch per pound in them, so you do have to be careful with that. And then I made a little mistake, which was this was off the screen, I know, where I was in MathCAD, the W's and the omegas. Let's see, where are some of them together? Here we go. Here's a W and here's an omega. They look very similar, and I had set up one of these as W sub-elements instead of omega sub-elements. So when I went to add it together, it didn't know what I was talking about. All right. I think that gets us all the information we need for critical speeds. This is test 3 type stuff. Test 3 is basically going to be springs. Exam 3. I think I already closed the Moodle page. No, it's right here. Exam 3 is topics 13 through 17, which are all spring related. So test 3 is basically springs. I'm still working on grading exam 2. You do have a score in Moodle on exam 2, but that's the automatic score from Moodle. I still need to go in and add all the partial credits parts, and I haven't done that yet. So get ready for exam 3 coming up shortly. I mean, you've got 2 weeks, but it's not that far away. We're getting close to the end of the quarter, I guess is what I'm saying. All right, I will see you guys on Wednesday. We'll talk about spring fatigue. It's actually not a very lengthy topic, but we'll talk about that. And then we'll finish up springs on Friday and go into some new things for a while. All right, I will see you.